describe the variation of the magnetic field strength when a current flows in a solenoid or a straight wire. And what does the direction of the magnetic field lines tell us? To answer this flashcard, we need to first sketch the pattern of magnetic field lines that are created when you pass a current through a solenoid or pass a current through a straight wire. Let's take a look at that to begin with. So with a solenoid, the pattern of magnetic field lines looks very much like a bar magnet, looking something like this. Now the question is, which side of the solenoid is which pole? So which one is north, which one is south? And here's a little trick you can do. So just put that away for the moment. Check out the direction that the current is flowing in. So here we've got the cell with a positive on the left, and so that means that current is flowing up this coil here and then going back down into the page. If you imagine that you're looking at that coil from this direction, from end on, then the coil would look a little bit like this. We'd see the sort of entry coil part coming up here on the right hand side. That's the one that's closest to us as we're looking at the page. So there's our current. Now the trick is, if you can fit a curly N, capital N, or a curly S with arrows that match the direction of this current, then that will be the pole. So in this case, we can match a curly N, and that matches the direction of the current. So we know that this side here is a north pole. You can do the same thing on the other side. Just again sketch the end-on view of the coil, which would look very similar. But this time current is leaving the coil, and here we can sketch a curly S with with two arrows on the end which match the direction of the current. And so we know now that we've got a north pole and a south pole. So let's put on the lines again. And we know that the direction of the magnetic field lines is always from north to south. From north to south. There we go. So these guys come in to the south pole, like so. Okay, now back to the question. Describe the variation of the magnetic field strength. So a key idea here is this. The closer the magnetic field lines are together, then the stronger the magnetic field. So that's very important, and this will apply to both the solenoid and to the straight wire. So here we can see that the lines are very close together inside the middle of the solenoid. So at this point we have a very strong magnetic field. Just put mag field. Lines are very close together. They're very densely packed. But up here they're not so densely packed, and so we have a weaker magnetic field. And so that's how you can compare the strength of magnetic fields just by looking at the lines and seeing how close they are together. Okay, right, what about a straight piece of wire? Let's take a look at the magnetic field around a straight conductor. Again, look at the direction that current is flowing. So here we have the positive on the left, so current is flowing from left to right. And here we're going to use a principle called the right hand grip rule, which looks a bit like this. So you point your thumb in the direction that the current is flowing, so that's from left to right. Wrap your fingers around as if you're holding the conductor, and the direction of your fingers, that your fingers curl, will be the direction of the magnetic field, which will be circular around the conductor. So let's put those on now. So we know that the direction is going like this, around the conductor, and that's a circular magnetic field. Now once again, take a look at where the lines are closely packed together. So here we've got a strong magnetic field, whereas a little bit further out it's much weaker. Okay, finally, the last question: what does the direction of the magnetic field lines tell us? The answer to that is that it is the direction of the force on a north pole of a magnet at that point. Let's write a few words about that. So the direction of a magnetic field is the direction of the force on a north pole at that point. So, important definition for you to remember. And that's why we can dangle a magnet on a piece of string, let's say here. And of course, magnets always come with a north and a south pole. So if we have a north pole there, a south pole here, the magnet will align itself. So the north is feeling a force along the magnetic field line. And that's why a compass will always point towards geographical north, which happens to be magnetic south. Finally, one last important piece to mention here is what happens if you increase the current and what happens if you change the direction of the current. Very simply, if you increase the current, the strength of the magnetic field increases. So the lines, you get more lines, more densely packed. And if you change the direction of the current, then everything reverses. Just the direction of the magnetic field reverses. So we can do a little table down here just to say if we increase the current, or if we change the current direction by turning the battery around or the cell around, then what happens to the magnetic field? Just put a little header here, magnetic field. Okay, and the answer is if you increase the current, the strength of the magnetic field increases, more lines packed together, and if you change the current direction, then the magnetic field direction also changes. And in the case of a solenoid, that means that the north will become a south and the south will become a north. It'll just flip over. Lots of information on that flashcard. Hope it makes sense, and I'll see you in the next flashcard.